Hello everybody, welcome to the ASNR Biomax session. My name is Markus and I'm telling you more about NICARA, our latest technology, and how you can use it to monitor the healing of connectomes after tumor resection. It is known from literature that patients with glioma very often suffer from cognitive impairments and show a decrease in cognitive scores across all domains, here indicated by the yellow shapes. Therefore, tumors may have a much larger effect on the brain than just the local effects of tissue damage. The way the tumor exerts its non-local effects and have an impact on cognitive decline across all domains is seen in connectome networks and white matter tract impairments. So here we have data from the literature showing, for example, the uniculate fasciculus and also the superior longitudinal fasciculus, which are significantly decreased in FA scores compared to matched controls. If we now look at, for example, the correlation between SLF FA score and visual spatial memory task performance, we see a clear correlation. That's why we believe that the connectome and white matter tracts are the structural correlate of cognitive decline in tumor patients. So clinically relevant questions you might ask are: how does brains rewire in response to brain tumors? How does a brain network change due to surgery? And is it possible to predict changes of surgery outcome based on connectomes? Of course, it's necessary to know how structural network changes are associated with cognitive functions. However, assessing the connectome is time-consuming, requires a lot of expert knowledge, especially in neuroimaging, and also needs large hardware resources. This often prevents doing connectomics in a clinical routine setting. Here's our solution. NICARA stands for Neuroimaging-Based Connectome Assessment in Research and Application. And the novelty of NICARA is that it provides fully automated processing routines for structural and functional connectome extraction. NICARA allows fully integrated study management and comes with nice visualization functions with methods to do assessments and to compare connectomes over time or between groups or between patients and matched controls. This is the typical workflow of NICARA. NICARA is a client-server application. You use it through your web browser. And the first thing you do is you upload your data sets, your raw imaging data sets here in the Nifty format to the server. The server can be in the cloud or can be hosted in-house behind the firewalls of your clinic. Then, after upload, processing routines are executed for probabilistic fiber tracking, for deterministic fiber tracking, but also for visualization. And the results you can see here. You see the T1 weighted image of a patient together with fiber density maps for every streamline, for every fiber tract. You can assess those fiber tracts in the feature space. So the feature space represents the information how strongly two brain areas, two regions of interest are interconnected. Strong lines are those indicated in black here, for example. You can use this information to do all sorts of quantitative assessments. For example, you can assess the connectome over time, do longitudinal assessments of the individual patient, but also compare the patient to matched controls. You then get a patient report, or you can do group-wise comparisons. Here's an example of a structural connectome pipeline that we execute by NICARA. All the tools we put together are open source. We select the best tools available in the market, those which are validated by hundreds of peer-to-peer reviewed studies. And the way we connect the tools in such a pipeline were already suggested recently as preferred neuroimaging method for Alzheimer's disease clinical drug trials. In addition to the processing pipeline, we also execute tools for quality control. Here's an example from the CAT toolbox that we are using and executing. So it reports nicely how the segmentation has been executed by NICARA to see if your image is of high enough data quality to allow for successful probabilistic fiber tracking. I now show you a nice first case study on tumor resection, the effects of tumor resection on the connectome. The data comes from the Virtual Brain Tumor Showcase, and the first example is a female patient belonging to the age range of 56 to 60 years, and this patient was suffering from a right hemispheric glioma. You first of all see the T1 weighted image. The right hemisphere clearly shows the tumor, and in addition to that you see a fiber density map. What is a fiber density map? A fiber density map indicates for every voxel the density of the fibers running through this voxel and belonging to a certain Roy to Roy based white matter tract. For example, here the superior longitudinal fasciculus, the SLF, in the ipsilateral side of the tumor and in the contralateral side. In the contralateral side you nicely see the color scale. Red voxels are those of a high fiber density, blue voxels have a low fiber density. So we then use our pipeline results to go from this image space visualizing this T1 weighted image to a feature space that represents the features, so the facts, the information, how strongly two ROIs are interconnected. Black thick lines are indicating strong connections, thin lines are weak connections. And if you compare the ipsilateral side and the contralateral side, you see already a more complex, a more dense connectivity network of the SLF compared to the ipsilateral side. But this of course needs further assessment, further quantification, and this is depicted in the next visualization. So this is a box plot with the gray lines indicating the gray boxes indicating the reference cases. So we have in this example just 11 matched controls, but still the variation is very small. And the orange line indicates the patient measurements. So at the x-axis you have all the fiber connections, all the combinations of regions of interest in this right hemispheric, so ipsilateral SLF white matter tract, and at the y-axis you have the connection strength. So what you see, and you can clearly, it appears really clearly that the patient has reduced fiber density in the strong connections throughout the SLF right hemispheric tract. So the question that we asked was, how will these connection strengths develop after tumor surgery? And here are the results. So what you can nicely see is that for all connections that were below the norm values of the reference group, we see a restoration of fiber densities. Some connections even increase their fiber densities beyond the reference scale, so they overcompensated to a certain extent. So in that sense, we can say that the patient benefited from the surgery by restoring, or as he restored the fiber tract, the white matter network, the connectome network, to original or control levels or even beyond. And you also see this in the longitudinal assessment. Here are the percentage changes, the percentage differences. So many connections increased by more than 200%. And in this left diagram, you see those connections with an increase and those connections with a decrease, indicated in red and blue respectively. If you look at the fiber density map after tumor surgery, we see that the tumor is gone. Basically here we see a nice fiber density map that it looks similar as in the contralateral hemisphere. I would like to give you a second example, same data set, the Virtual Brain Tumor Showcase, and in this case it's a male patient in the age range of 61 to 65 years with a right hemispheric glioma as well. And if we look at the T1 weighted image and the fiber density map, we see again nicely the tumor. We see the fiber density map, which is reduced in its expression compared to the contralateral side. Again, this 3D lattice graph with a more dense and complex network in the contralateral hemisphere compared to the ipsilateral hemisphere where the tumor is located. If we now look at the assessment, patient versus controls, we again see a similar pattern as in the first patient. So we see a reduced fiber density in many of the connections, perhaps not so extremely expressed as in the first case, but still clearly visible. And if we now look at the results after surgery, we can see if the patient benefited in terms of a healing connectome after surgery. And we see that indeed most of the connections have returned their strength in a reference regime, a reference range from the matched controls. Some connections also overcompensated. This is reflected by the longitudinal representation. Here we see a strong increase, not as many connections as in the previous case, but still a significant amount of connections, a vast amount of connections have increased their fiber densities. Only a few have reduced connection strength. And this is also seen in the fiber density map. So we have red spots now here in the fiber density map indicating a high fiber density, which was not seen in the diagram, in the picture before surgery. I would like to give you another example, the same patient but a different fiber tract, this case the Cingulum fiber tracts. If you look here in the T1 weighted image and at the streamline, now it's a coronal section, you see that the white matter tract here, the Cingulum tracts, are distant from the actual tumor. So we wouldn't expect too much of an effect, but let's see how it comes out in the assessment. And interestingly, that even the remote fiber tracts, or the remote connections here, show a little reduction in strong connections here. If we now look how these connections changed after surgery, we see that those connections which were slightly reduced have returned to normal levels. Some even got stronger than the reference levels. And this tells us that even white matter tracts remote from the tumor suffer or have reduced fiber densities before surgery and show a nice compensation, as indicated here by the percentage increase or the colored 3D lattice graph. And this tells us, taking these results together, that NICARA and the pipelines we are using are very sensitive in monitoring connectome changes before and after tumor surgery. We found reduced fiber densities in the individual patient in major white matter tracts in close vicinity and in more remote white matter tracts to the brain tumor. And after after tumor resection, fiber densities of these white matter tracts normalized again. This is an interesting finding. We must admit that we cannot clearly say if the reduced fiber density is actually due to a loss of fibers or more caused by a pushing of the tumor so that the fiber tracts are squeezed in a way or pushed away and therefore are less visible or less detectable by DTI tractography. Even though this cannot be fully answered by this first pilot study, we still believe that a situation in which the fiber tracts of a patient are pushed in this way and are not detectable by DTI tractography are not a good situation, because fiber tracts, axons that experience such a mechanical stress are at high risk to degenerate, and this is a situation that in any case should be resolved. And by monitoring these DTI tractography changes with NICARA, we have an additional opportunity to monitor the outcome of a brain tumor resection. So it should be of value in clinical application. So in any case, NICARA is of a certain worth to neuroradiologists and neurosurgeons, as NICARA is the first compelling solution for automated processing, visualization, and connectome and morphometry assessments in the same program. NICARA provides, as we demonstrated, additional monitoring opportunities for tumor surgery based on quantitative connectome assessments. NICARA will save your time that you do not need to invest on processing pipelines for DTI tractography or fMRI resting state analysis that you can now spend on your patients, on your actual research questions, and the automated pipelines in NICARA do the job for you. Moreover, NICARA saves your money because we provide the elaborated hardware resources needed for DTI tractography assessments. And with this, I would like to thank you for your interest. You can register your free demo account in NICARA via nicara.eu, and we are very happy if you reach out to us via nicara@biomax.com for questions, for your feedback, or further scientific discussion or interest in the product. Thank you very much, and goodbye.